All right, so this is the first video in chapter 12, which has to do with complexation as it pertains to analytical measurements. So if you've taken an inorganic course like Chem 275 or 475, you will have already learned about the sort of chemistry and the chemical mechanisms that relate to coordination, which is the process by which complexation operates through. I'll give you another disclaimer. So if you watched the end of the previous videos, I mentioned that I just had eye surgery. That's true still, because I'm recording this video in the same day. So you may see my right eye close or not open or tear up. Disregard that. I just had a superficial keratectomy, which is where they remove the entire epithelium of your eye and then they polish it down. It's quite painful. If you look at images on the internet, you'll see how uncomfortable you can imagine such a procedure is. So my eye is pretty sore and I can't see out of it. But it's functional enough for me to walk through this. So what I've got in what you're seeing here are just examples of a couple ligands or molecules that can bind quite tightly to positive ions in solutions to form these things called complexes. And that's the basis of this chapter. We're studying less the mechanism, as I mentioned, but thinking more about leveraging this type of chemistry for chemical analysis, for measuring things. And so in this case, EDTA is one example of a multidentate ligand, dentate coming from the Latin root for teeth. So these ligands, they essentially surround a metal ion, like in this case manganese 3, and you can see manganese 3 is right in the center here, and it forms, or it bites into, that's where the dentate comes from, it coordinates, or it adds 2 electrons from each one of these carboxylate ions as a Lewis acid in this case, or a Lewis base, and it comes together and coordinates and sort of forms a cage and wraps itself around that manganese ion very tightly. And of course, the more ligands that a particular molecule has, in this case EDTA has 4, the stronger that chelation process will be. Also, the more positive and smaller of metal ions, again, the stronger that binding force will be, that complexation. And so if we understand the stoichiometry of these types of complexations, because they're so strong, the equilibrium constant's very large, and we can use these to quantify things like metal ions in solutions. So we essentially can do like an acid-base titration where we dose in a certain amount of EDTA through a burette volumetrically and use some indicator to tell us when we've reached equivalence. Equivalence in this case being we've added exactly the right amount of EDTA to complex out this metal ion. ATP is an example of a tetradentate ligand. In this case, you can see how ATP, again, ATP is a biochemically relevant or biologically relevant ligand that we use as part of the process in which we generate energy in the body. You can see how it complexes metal ions in a certain way as well. As a complete aside, just because I find this to be fascinating, but chelation and this notion of using molecules to encapsulate or capture metal ions in the body has an interesting history with pseudoscience. There is such a thing as chelation therapy, and it's actually really common, not just for, well, I'd say for 2 different things. One is if you inadvertently poison yourself with metal ions, and if you go to the doctor, if they know that you've been poisoned with metal ions, things like mercury or lead or iron like is shown, or even arsenic shown in the top right, if they dose you with a particular chelation agent, sometimes it actually is EDTA, at a certain pH, then those metal ions will be complexed and neutralized in a way that they can pass through your urinary tract rather than incorporating themselves into key proteins, enzymes, or even DNA, in which case that causes damage to your body. And so chelation therapy is a pretty common mechanism by which doctors will remove poisons from the body, metal ion poisons from the body. It can also be used to remove plaque from an artery. So this bottom portion is just taken from Shutterstock, but it is a mechanism by which certain plaques, depending on the chemical composition of those plaques, can be complexed out. They can be essentially added as part of an equilibrium, and if you add enough EDTA, it starts to pull the equilibrium towards complexation and can clean out arteries in non-invasive ways. So this would be a chemical mechanism to attempt to clean out arteries. Of course, this is going to depend on how calcified those plaques are, but this is usually a first pass before they end up having to do more invasive treatments. What I mentioned or alluded to pseudoscience is this interesting thing. This comes from the internet, from I'mSimplyADad.com, but if you just look up chelation therapy, there's all sorts of interesting pseudoscience around things like autism, right? Autism, because the mechanisms that produce autism aren't clearly established right now. There's a lot of origin stories for autism, like vaccination, but also this idea that potentially heavy metals and things like that can produce autism in children, heavy metals from drinking water or else. And so chelation therapy is something that can be prescribed in a way that it could potentially mitigate autism. Not in reality, there's no correlation there, but in this sort of pseudoscience world. So there's lots of analytically useful chelating agents. These just come from your textbook, EDTA being the most common by far, just because it's quite soluble, and because it depends on how you want to think about this, but it could be either considered a tetradentate or even a hexadentate ligand. You can see it's got these 4 carboxylic acid groups, but it also is a diamine. So on the right pH, this species could also have positive chelating effects, positive ion chelating effects. Nitryllotriacetic acid, NTA, is another really common multidentate ligand. This is one that I mentioned in the previous video where I walked you through the use of hydromedusa for producing alpha diagrams for EDTA. NTA is also, the equilibrium constants for that are also in hydromedusa, which is really nice. There's a couple other species here that are a little less common, but you will find in some analytical procedures, especially older wet chemical procedures. So this chapter is really focused on EDTA and EDTA alone, and that's because it's, as I mentioned, the most analytically relevant and useful, and you'll see EDTA in so many different solutions. In fact, for those of you who are biochemically oriented, Dr. Nina Grover, in her research lab, does EDTA titrations all the time. If you go do research with her, if you already have, you'll know this. She is interested in studying the interactions between metal ions and RNA. And in order to do that, she needs to understand where those ions are in the RNA species. So what she does is take small concentrations of particular RNA geometries or moieties with these loops on them, and then she doses it with a certain amount of metals. And you can then titrate the system with EDTA in a microcalorimeter. And what happens is every time you pull off one of those metal ions from an RNA helix or coil, it'll change the configuration slightly, and that will change the amount of energy either required or released, and that will be measured by the calorimeter. So it's sort of a synchronous analytical experiment where you're doing a titration, so you know exactly what concentration of complexing agent you've added, or really the equivalent of metal ions being removed, but then you're also associating that with the energy change in the system, which then allows you to correlate something to the importance of the location of that metal ion, where it was, how many equivalents were bound, and how critical it was to, say, the geometry or the folding of that RNA species. So I showed you a plot like this, or similar to this, that was generated using Hydra and Medusa. This is just an alpha diagram of the molecule shown down here, of the EDTA molecule. And so you can see at low pHs, at the very lowest pH, you have something that's fully protonated, which we call the H6Y2+, Y being essentially this base molecule. And then, of course, as you go to higher pHs, you're going to pull off that first proton. And then as you pull off that first proton, you grow in the H5 complex. And then as you yank that off, you grow in the H4 and then the H3. All of these pKs for the first 4 pKs, they're all fairly close to each other. You can see pK 1, 2, 3, 4, all below 2.69. So those species are all overlapping with each other considerably, just based on the nature of how close those pKa values are. But once you get to pK 5, there's a almost 4 order of magnitude jump, and so there's a lot more space in generating the next species. H2Y2-, so that's the 2- ion, and then you have the pK5, which is the H3 minus, and then you have all the way out here, once you've fully deprotonated the HY3- complex, you have the Y4-, and that's above 10.37 here. So there's lots of different species present which are clearly pH dependent. So at any given pH, we could extract the alpha, or the fractional composition, of any species. So for instance, if we wanted to know the fractional composition of the Y4- species, we'd write that up as alpha Y4-, and that would be very similar to what we did with the fraction of different acid and base species. Here, that would be the concentration of Y4- species divided by all of the other EDTA species in the system, which, of course, you could write sort of a mass balance equation. That would be the concentration of all of them. So H6Y2 plus H5Y plus, etc., all the way up through the Y4-. And so it would just be the fraction of that species in solution. This, of course, when we're talking about just having EDTA in solution, this is true. Once you throw a metal ion in solution, this is also true. Say we throw in calcium 2+. This fraction is still true, but when we write the Y4-, what we mean is the Y4- that's not bound to anything. And when we write EDTA, we also mean the fraction of those things that are not bound to calcium. But this is still true, the fraction of EDTA in that particular form. That all becomes relevant here shortly. So this is another way to just write that explicitly. So the fraction of Y4- is the concentration of Y4- all over of the concentration, the sum of the concentrations of everything. But what you'll often see, and what I'll write, is instead of writing out all of those species like this, we'll just write out EDTA, but it's implied that the concentration of EDTA is really the formal concentration of EDTA, which includes all of its species, the concentrations of which, of course, are going to be pH dependent, clearly based on an alpha diagram that's like this. So just to be super explicit here about the meaning of an alpha fraction, in this case coming off a diagram like this, I just grabbed an example from your textbook, which says, what does alpha y4 minus actually mean? So the example here says the fraction of all free EDTA in the form of y4 minus is called alpha y4 minus. When they say free EDTA, they mean non-bound to a metal ion yet. So they don't mean like pure EDTA, they mean some species of EDTA, but they mean that it hasn't been bound to a metal ion. It's just by itself floating around in the solution. So at pH 6, at a formal concentration of 0.1 molar, again, formal concentration means the concentration of all of the EDTA. So 0.1 molar for EDTA, remember that's the sum of all of the different species of EDTA. They're talking pH 6 here, so that's somewhere in this range where this red line is. The composition of an EDTA solution is such. And so they give you all of these species in their relevant concentrations. And the notion would be to compute what the fraction of the Y4 minus compound is under these conditions. And so remember the fraction or alpha Y4 minus is going to be the concentration of Y4 minus unbound in this case, and we know it's unbound because that's what we're given, divided by the sum of all of the individual EDTA species concentrations, which were given 1, 2, 3, 4, 5, 6, 7 different concentrations here. And we can sort of anticipate, right? We're given these numbers, so really all that would be to take all of these values, sum them up, and then put them in for that value, and then take the y4 minus and put it in for that value. That would give you literally what fraction of y4 minus is unbound at that concentration of 0.1 molar EDTA and at pH 6. And we can look at this curve. The alpha diagram is not going to change, right? It's a fixed sort of idea based on pH dependence and all of the relevant pKa's of the system. So at a particular temperature, this is a fixed system. So at pH 6, we can look and say, well, what's the dominant species? Well, we'd expect probably the H2Y species to be the dominant one, and probably the HY3 minus to be the one that's next most dominant, because you essentially have a buffer system with those two being the dominant buffering species. And we can look back at our numbers here and you'd say, okay, H2Y2 minus, yep, that is the highest concentration, 0.057, simply because we know that from the curve, and probably HY3 minus, which is right here, will be the next highest, and it is 0.043, and then everything else is going to be in quite low concentrations, especially the Y4 minus. That's in the 10 to the minus 6 range, because you can see its pKa doesn't really come into being until roughly 10.5. So this is quite low. So we can compute this, and that tells us the fraction of Y4 minus at pH 6 is 1.8 times 10 to the minus 5th. So it's a really, really small amount, which makes a lot of sense because we're at quite acidic pHs. And it's not that this is important for you to be able to calculate this. That's not really why I'm doing it. Just to give you a more explicit sense of what this means. What do we have in solution at that moment in time? And at this point, the Y4 minus species is a really low concentration.